So the core idea of the capacitor is that you've got two metal plates that can hold lots of charge. There's plenty of space for extra charge on this large metal plate, and a layer in between that charge cannot cross, typically either empty space or glass or plastic, some layer that insulates, some layer that prevents charge from crossing. And if you hook this up to something like a battery, with positive terminal and negative terminal, what's going to start happening?
Charges will accumulate onto the capacitor until it has until it's fully charged.
Right, you're going to get charge starting to accumulate. This positive terminal makes positive charge start accumulating here. And physically what's going on is this positive terminal is pulling electrons out. A negatively charged electron gets attracted towards this positive terminal. And of course, each plate consists of lots and lots of protons and lots of electrons. There's always plenty more protons and plenty more electrons, but they're balanced in numbers, same number of protons and electrons, so the plate is uncharged, neutrally charged. If you pull out some electrons, there's some positive charge left over. Meanwhile, electrons are getting repelled from the negative terminal of the battery, so electrons build up here, which we would treat as negative charge. So positive charge physically means not enough electrons. Negative charge physically means too many electrons. So as charge accumulates though, let's say you've got one more electron that you're trying to push in. So here's one more electron. The battery's negative terminal is pushing it towards the capacitor. But meanwhile, what else is happening to it?
Is it pulling a proton from the other side?
Well, the positive terminal is also pulling on the electrons. The protons don't actually move. We usually treat current mathematically as the flow of positive charge, but physically it's the negative charge, the electrons that are moving. So we also might have an electron over here that's experiencing a pull from the battery. So this electron is being pushed by the negative terminal of the battery. This electron is being pulled by the positive terminal of the battery. So we'd say electrons are moving counterclockwise, although we would describe current as flowing clockwise. Because the electrons are, the motion of electrons is motion of negative charge. Current, mathematically, is the flow of positive charge. And negative charge moving this way can be treated mathematically as positive charge moving this way. So we'd say current is flowing clockwise because the negative charge is moving counterclockwise. So the positive charge is not physically moving. The protons are just staying still. But electrons moving counterclockwise can be treated as current flowing clockwise. However, as these charges move, like this negative charge is being pushed by the battery, but also it's approaching this plate with negative charge. What would the negative charge already on the capacitor do to this electron?
Repel?
Yes.
Repel?
The negative charge, or like charges, repel each other. So this electron with negative charge gets repelled by the negative charge already on the plate. So we get a push from the capacitor. And note that those are opposing each other. The battery is trying to push more charge into the capacitor. The capacitor is pushing back, saying we don't want any more charge, we already have charge of that type. Same thing over here. This negative charge, this electron is getting pulled by the battery's positive terminal, but it's also getting attracted to the positive charge already on the capacitor. So we get a pull from the capacitor as well in opposing directions. And what do you think is going to determine, like we know that the push from the battery, the pull from the battery, those should be constants because the battery has a constant voltage, epsilon. Delta V for the battery is plus epsilon, which is a constant. But what do you think the push or pull from the capacitor is going to depend on? What's going to determine how
Will it
strongly
depend on
the capacitor pushes on this charge? What was that?
the net charge of the capacitor?
Yeah, the charge on, specifically the charge on each plate individually, which should be the same but in opposite signs. The amount of charge on the capacitor so far determines how strong that push is. So the way we describe this mathematically is we say that the capacitor has its own voltage, and that voltage, that push from the capacitor, is proportional to how much charge is already on it. So the capacitor exerts its own voltage, representing that push, and that's proportional to the amount of charge that's already on it. The amount of charge stored on the capacitor so far. So if there's no charge at all, there's no pushback. Charge can flow easily. As a little bit of charge builds up, then there's a little bit of pushback, and it's a little bit more difficult for charge to flow. The current gets a little bit slower. As more and more charge builds up, as you get more and more charge, the pushback or pullback from the capacitor gets stronger and stronger. So what would you expect to happen to current?
Then the current would stop, right?
Eventually it'll stop. Over time, it slows down, and approaches a complete stop. Eventually, you would get no current at all if the pushback from the capacitor matches the push from the battery. If those pushes match each other, if those voltages balance out, then there's no current at all. In fact, this is really easiest to see, I think, if we also have a resistor in the circuit. If there's no resistor, then this all happens instantaneously. No resistor basically means you get infinite current for zero amount of time. The capacitor instantly fills up. But if there's a resistor, then that slows down the current or limits the current. So that means that the charge doesn't move instantly. It takes time for the capacitor to fill up. And it actually is very helpful to look at the loop rule here. If we write out a loop rule for the entire circuit, the sum of all those delta voltages in that loop would have to add up to what?
To 0.
Yeah, any complete loop, the voltage differences have to add up to 0. And we can expand that to delta V from the battery plus delta V from the resistor plus delta V from the capacitor equals 0. Battery is always plus epsilon. And what about the resistor? What's our usual delta V for the resistor?
Minus IR.
Yeah. The negative IR from Ohm's law. And for the capacitor, we are going to need to use this fact that delta V of the capacitor is proportional to charge stored. So this is going to be something times charge. Because any proportionality, if delta V is proportional to charge, that means delta V can be written as equal to something times charge. Or alternatively, that charge equals delta V times something. And the way we write that proportionality is we write it as charge equals this constant times capacitance times delta V. So we're basically defining this new property called capacitance. Capacitance is a property of these plates, and specifically it depends on the cross-sectional area of the plates and the distance between them, and also what material the interior is filled with. So those properties determine the capacitance. And capacitance is just this constant of proportionality that you multiply by the voltage difference to turn it into the charge accumulated. So what would, for instance, what would a very large capacitance mean? If capacitance is very large, what would that tell you about these other variables?
Charge is
If sorry, go ahead.
No, I was just gonna say the charge is large.
Yeah, if you've got a lot of capacitance, that means the charge is very large compared to what other value?
The voltage?
If you want to talk about very large, it's got to be really compared to something else. Like, for instance, the Earth is very large compared to me, but very small compared to the sun. So if you're saying that large capacitance means lots of charge per what? Or lots of charge compared to what other value?
The voltage?
Yeah, compared to the voltage. High capacitance means you get lots of charge per volt. Or alternatively, that it only takes a little bit of voltage to get a certain amount of charge you want. The idea is that the more voltage you apply to the capacitor, the more charge builds up. If you've got like a 1-volt battery, you'll only build up a little bit of charge. If you've got a 10-volt battery, you'll build up 10 times as much charge, after enough time anyway. But the capacitance can be thought of as this almost like a conversion factor that converts how much voltage you apply into how much charge will accumulate, given enough time. In fact, it's often useful to look at this as a ratio or a rate of change. That if you solve for C here, just dividing by delta V, you get Q over delta V. So capacitance can be thought of as the ratio of how much charge per volt, the amount of charge the capacitor would store per volt of the battery attached to it. So for instance, if the capacitance is 3 farads, farad meaning coulomb per volt, 3 farads would mean it stores 3 coulombs if it's attached to a 1-volt battery. Or 30 coulombs if it's attached to a 10-volt battery. The ratio would be the capacitance, the ratio of how much charge it stores divided by how much voltage is attached to it. And the units for that is farads. 1 farad being 1 coulomb per volt. Farad equals coulomb over volt. Because we've got to have capacitance measured in charge over voltage. So that's going to be farads, which is coulombs per volt. So that's the unit of measurement we're going to use for capacitance. Any questions on that so far?
Oh, no, thank you.
And also, if we solve this for voltage, because what we really care about is voltage, how would you isolate delta V capacitor here?
Q over C.
Yeah, we just divide by C, we get Q over C. So that is our formula for voltage of the capacitor. Delta voltage of a capacitor is the inverse of capacitance times charge, or just Q over C. That's how it would be written. And we also usually write that as a negative also, negative Q over C, in the sense that the capacitor is not trying to pull charge into itself. The capacitor is trying to push back against charge entering it. In this context, the capacitor is pushing back against the battery. But more broadly, the capacitor's voltage is acting in a direction, it's pushing in a direction to try and prevent charge from coming into itself. Or if it's discharging, if the capacitor is already full and the charge is being allowed to leave, the capacitor is pushing in a direction to remove charge from itself. So that's what the negative signifies here in terms of direction. The push from the capacitor is a push against getting more charge. It's a push trying to prevent getting more charge. So we can use this as our delta V for the capacitor in the loop rule equation. Negative Q over C. So there's our loop rule equation. Epsilon, the voltage of the battery, plus negative IR, the voltage of the resistor, plus negative Q over C, the voltage of the capacitor, adds up to 0 because it's a complete loop. Any questions on that so far?
No.
And a very convenient way of writing this, now that we've got this loop rule, is to add the negative terms to both sides. So we get IR plus Q over C equals epsilon. That is the voltage that the resistor uses plus the voltage that the capacitor uses adds up to the voltage available from the battery. Explain what the negative sign signified. Yeah, the negative sign in this capacitor formula signifies direction. That the push from the capacitor, because voltage is basically just an electrical push, the push from the capacitor is in the direction opposite to gaining more charge. So you can interpret Q, in terms of direction, you can interpret Q as the direction of gaining more charge on the plates. The capacitor is pushing back against getting more charge. So the negative sign is representing that opposition, that the capacitor is pushing against the direction of getting more charge, or pushing in the direction of losing charge. So the direction of voltage is in the direction of decrease in charge of the capacitor. Left to its own devices, the capacitor will push in a direction to cause current to flow out of it, causing itself to lose charge. Any questions on that so far? And this is very similar to a spring in a lot of ways. If you look at the force of a spring, negative kx, this is just saying the more you compress the spring or stretch the spring, the more the spring is displaced from equilibrium, the more force you get. And this negative sign also represents direction. If you compress the spring, pushing it in the negative x direction, you get a force pushing back in the positive x direction. Or if you stretch the spring, pulling it in the positive x direction, you get a force pulling back in the negative x direction. The force is opposite to the direction the spring is displaced. And the capacitor behaves in a very similar idea. The push from the capacitor depends on how much charge is already on it, but the push is in the direction of opposing that change in charge. Same idea for a spring. The force on the spring, the amount of push, is proportional to how displaced it already is, with a negative sign representing that the force is trying to push back towards equilibrium. In this case, equilibrium would be an empty capacitor. So the voltage on the capacitor is trying to push or pull back towards the capacitor being empty. Of course, it can't do that because the battery is also pushing even more strongly to fill it up. But in this context, at least, these equations matching up so similarly that push equals negative something times displacement means that the capacitor acts very much like the electrical version of a spring. You push on it, store some charge in it, and the charge that's in it pushes back, trying to restore the equilibrium. Any questions on that so far? All right, so let's see what else we can do with this, this voltage equation here, that the voltage from the resistor plus the voltage on the capacitor has to add up to the voltage of the battery. And a very useful way of thinking of this is that it's saying that the battery in this circuit, the battery is able to do two things. The battery is able to provide voltage to the resistor, which makes current flow, or the battery is able to provide voltage to the capacitor, which causes charge to be stored. The resistor getting voltage means current is flowing. The capacitor getting voltage means charge is being stored. But there's a limited amount of voltage available. There's a limited amount of epsilon. So maybe the battery is doing lots of one and only a little bit of the other. We might be looking at a situation where the battery is causing lots of current to flow, but only a little bit of charge is being stored in the capacitor right now. Or maybe the capacitor is storing lots of charge, but there's nothing left over for the resistor, so the current is flowing very slowly. Or maybe there's some of both. Maybe there's a medium amount of charge being stored and a medium amount of current flowing. But note that the battery cannot do lots of both. You can't have lots of charge being stored and lots of current flowing. And you also can't have none of both. You can't have no charge stored and no current flowing because that wouldn't add up to epsilon. Unless you've got no battery at all, then that would be possible. But these two terms have to add up to epsilon at all times because the battery is providing a constant amount of voltage. Any questions on that so far? So let's take a look at what that would look like on an actual graph. If we were graphing, for instance, current and charge. We're assuming we're starting off with how much charge on the capacitor.
Would it be 0 charge?
Yeah, let's assume we start off with the capacitor empty, 0 charge, no charge at all. So the capacitor starts off at 0 charge. And if we have no charge, what does that tell you about the current?
The current must be high.
Yeah, we're going to get a very high current. In fact, we're going to get the maximum current. Let me put this equation up at the top so we got some more room to work with. And it's very useful in cases like this to look at what's going on at the beginning and what's going on a little later and what's going on after a long time. So if we take a look at the start, at time t equals 0, the very beginning, capacitor is empty, Q equals 0. No charge means we should expect lots of voltage available for the resistor because the capacitor's got no pushback at all. So we should expect lots of current. And we could even find how much current. If we just plug in 0 for charge, what's left in the loop rule? What does the loop rule become when we replace Q with 0?
Just epsilon over the resistance.
Yeah, because all that's left is IR equals epsilon. So current is going to be epsilon over R. So that's the initial current. Let's say I sub 0, the current at time 0. So that's going to be the initial current, and that's going to be the highest the current can get. Epsilon over R. So that's the current right now. But what does current mean? What's the formal definition of current?
Charge per time.
Yeah, charge over time. Specifically, change in charge over change in time. Formally, we'd call that a derivative. How much charge flows past that point per second. Which means the value of current tells you the derivative of charge. And that's a very important relationship because that's exactly what ties these two graphs together. Value of current tells you derivative of charge. And what does a derivative tell you about a graph?
The slope.
Exactly, the slope. So if we currently have a very large positive current, that means the charge has to have a very steep positive slope. The charge is increasing very quickly because current is flowing so fast. But now, a little bit later, we now have some charge. If charge now has a non-zero value, if charge is now a positive value, what does that tell you about current? If they've got to add up to this constant epsilon and charge has increased, what else has to happen?
The current.
Current decreases.
Exactly. The current's going to have to decrease because these terms still have to add up to a constant value. So charge increases, current decreases, not by the same amount, but by the same proportions. Because the extra multipliers, the R and the C, modify the amounts. But we at least know if charge is increasing, the current's going to have to decrease. And since charge is increasing pretty steeply, current is going to decrease pretty steeply also. And at this point, there's now not so much current. Current being weaker, well, the current is still positive, so the charge is still increasing. But since the current is weaker, the charge is going to be increasing more slowly. So this graph is going to get less steep. And at this point, the charge is still increasing. More charge is going to mean slower current. But since the charge is increasing more slowly, the current is going to be decreasing more slowly as well. Still some current, but not as fast. So current charge is still going to be increasing, but not as fast, less steep. And these keep getting flatter and flatter. Eventually, we're going to get to, let's say, after a long time. Mathematically, we'd be talking about the limit as t approaches infinity. Although in practice, this may take anywhere from a fraction of a second to a few seconds to a few minutes to a few hours, depending on the properties of R and C exactly. But after a long enough time, what should we assume about the current after a long time?
It's going to be 0.
Yeah, eventually the current becomes 0. Because we should expect that at some point the capacitor is going to be full. And by full, we basically mean it's not charging up anymore. No more charging up means no current. The charge has reached its final equilibrium value. No more change means no more slope, means no more current. So after a long enough time, the current comes to a stop, or at least close enough to a stop. Current is approximately 0. You fill in 0 for current, and what does your loop rule equation become?
Q over C equals epsilon.
Yeah. The entire loop rule just becomes Q over C equals epsilon because we're ignoring current now. We're assuming current is 0. And we can now solve that for Q just by multiplying by C. So epsilon from the battery times the capacitance of the capacitor equals the final value of Q that it approaches, which we usually call Q max. So that's going to be some asymptotic value. Mathematically, it never reaches it because the closer it gets to Q max, the slower the current gets. So formally, it'll never reach it, but it eventually gets close enough that it may as well be at Q max. So Q max is this asymptote equal to epsilon times C, voltage of the battery times capacitance of the capacitor. And meanwhile, the current is dwindling towards 0. Again, it formally never reaches it. It just gets closer and closer as an asymptote. But we at least know what the values start at and what both values, current and charge, what they approach as time approaches infinity, as we go on after a long time. Any questions on the calculations there so far, or the graphs? And based on these graphs, what sort of function does this resemble? If it starts off at some finite value and then approaches an asymptote, what function is that?
Exponential decay.
Yeah, this looks very much like exponential decay. For the current, we've got exponential decay towards 0 from above. For the charge, we've got exponential decay towards Q max from below. But they both count as exponential decay because they're both approaching some asymptote. And in order to figure out the patterns of that exponential decay, first of all, if we want to just look at how or why it's exponential decay in the first place, if we go back to, and before we do that, by the way, for exponential decay, I usually find it useful to try this approach. Anytime you've got something that you know or suspect is going to be exponential decay, a good way to start analyzing that is to look at what's going on at time 0. That tells you a starting point. And what's going on after a long time. That tells you the asymptote that it's going to approach. If you know the starting value and the asymptote it's going to approach, then you already know most of what you need to know about the graph. All you really need to know beyond that is how fast it approaches the asymptote, using the idea of half-life or time constant. But let's take a look at the mathematical details of that equation. Going back to our loop rule here, IR plus Q over C equals epsilon. If we actually fill in dQ over dt for I here, we get dQ over dt times R plus Q over C equals epsilon. And that means we now have a relationship between a function, Q, and its derivative, dQ dt, and this forms a differential equation. So if we can solve that differential equation, then we have a value for Q. Any questions on that so far? And to make this differential equation a little easier to solve, let's make a few algebraic simplifications first. First of all, instead of looking at Q, because the fact that Q is approaching this non-zero asymptote makes things more complicated. If we focus on current instead, we can change charge into current by just taking the derivative of both sides, because current is the derivative of charge. Derivative of current is just going to be I prime, or di dt. And then R is a constant multiplier, so it stays where it is. And what's the derivative of charge? How do we describe how fast current is changing?
Current? Oh, wait, never mind.
Derivative of charge is exactly current.
Oh, it is. Never mind.
So that means we can just replace dq dt with current. We still have the divided by c because that's a constant. But yeah, in general, derivative of I, we just write as I prime. I don't think that has its own separate term for it. But derivative of charge is exactly current. So we can make that substitution. dq dt is current. And then the voltage from the battery is a constant. What's the derivative of a constant?
0.
Right. So this becomes a much simpler differential equation. We just have something times the derivative of current plus something times current equals 0. And if we rearrange this a little bit, let's say we subtract I over C from both sides and divide by R, we find that the derivative of current is negative current over RC. Or an even more useful way of writing that, if we just split out the RC as a fraction. So the derivative of current is negative 1 over RC times the current itself. That is, derivative of the function is negative some constant times the function. And that always leads to what sort of result, what sort of function? In any situation where you know that the derivative equals a constant times the function itself, what's the only function you know of that behaves like that?
Oh, exponential.
Yeah, this has to be exponential. And this is a general rule in the study of derivatives, that if if y prime, if the derivative of y with respect to t, doesn't have to be y and t, it could be any variables. If the derivative of some function with respect to its independent variable is a constant times the function itself, and we usually use lambda for that constant, then that function has to be e to the lambda t times some coefficient, which is typically the starting value of y, y0. So we can make the same, we can conclude the same result here. Lambda in this case is the negative 1 over RC. Or sometimes we put a negative in these and say lambda is 1 over RC. But either way, we get current equals e to the negative 1 over RC, that's the constant here, times t, times some coefficient, which turns out to be the starting value of current, I sub 0. Or we could even fill in the starting value of current we found, epsilon over R, times e to the negative 1 over RC, times t. So that is our formula for the current. We now have a formula describing the current at any time. Any questions on that so far? And note that that's true regardless of what the strength of the battery was. If we had started with a stronger battery or a weaker battery or no battery at all, the derivative of the battery is 0. So we'd still get current equals starting current times e to the negative 1 over RC times t. So this is going to be true no matter what the battery is, or even if there isn't a battery. If you've got a capacitor discharging, like let's say you just connect a capacitor and a resistor and no battery. If the capacitor is already full of charge and there's no battery, the capacitor is going to discharge. Current is going to be leaving the capacitor until it eventually becomes empty. Any questions on all that so far? Also, now that we have a formula for current, how can we figure out information about how fast it's decaying? I mean, we could just start plugging in numbers. If we had values for epsilon, r, and c, we could just start plugging in values of time and figure out what's the current at each of those times. But if we wanted to figure out something like how long does it take to decay a certain amount, what aspects of this exponential decay function tell you how fast it's decaying? How could you tell just from looking at this equation the rate at which it's decaying towards zero? For example, if we had, let's say, two exponential decay functions, if you had like y equals e to the negative t over 2 and y equals e to the negative t over 100, they both start off at the value 1, because if you plug in 0 for t, you get 1 for both of them. E to the 0 is 1. But which one of these would you expect to decay faster? If you want to figure out how fast it's decaying, a very useful thing to look at is how much time does it take for the exponent to reach a certain amount. And a very convenient reference point is just for the exponent to be negative 1. Like in order to reach negative 1 here, how much time would it take for the exponent to be negative 1?
2.
Yeah, 2 seconds or 2 minutes or 2 of whatever the time, the unit of measurement is. Let's say these are seconds. I'll actually fill in s here. So for this equation, this function, it takes 2 seconds to reach e to the negative 1 as the final amount. How much time would it take for this one to reach that same value?
Takes 50 times as long.
Yeah, it's going to take 50 times as long. It'll take 100 seconds for this to become e to the negative 1. We call that amount of time the time constant. Time constant is amount of time it takes. Formally, it's the amount of time it takes to reach 1 over e of the original value, which is about 37%. And there's nothing special about 1 over e, it's just a convenient reference point because we're using e as the base of all these functions. And to get to 1 over e is equivalent to what e to what exponent?
The negative 1.
Yeah, this is equivalent to e to the negative 1. So we define time constant as the amount of time it takes to reach 1 over e as the original value. But you can also think of it as the amount of time it takes for the exponent to become exactly negative 1. The time it takes for the exponent, specifically the exponent on e, to become negative 1. So in this case, the time constant will be 2 seconds. You plug in 2 seconds for t, you just get e to the negative 1. In this case, the time constant will be 100 seconds. You plug in 100 seconds for t, you get e to the negative 1. So this is a convenient reference point. We can say that at that amount of time, the function has decayed a significant amount. Specifically, it has decayed to 37% of the original value, which is very similar to what other concept? What's another amount of time that it takes to decay a certain fraction? What if we replace this 37% with 50%? What do we call the amount of time it takes to decay to 50% of the original?
Half-life.
That's just the half-life, right? So the time constant is a very similar idea to the half-life. It's just different percentages. The half-life is the amount of time it takes to decay to 50% of the original. The time constant is the amount of time it takes to decay to 37% of the original. Again, nothing special about 37%. It's just that 1 over E is a convenient reference point. Then again, there's nothing particularly special about 50% either. It's just that 1/2 is also a convenient reference point. So time constant and half-life are just two different ways to parcel out the amount of time it takes to decay a certain amount. In this case, we can also look at the time constant. Time constant is going to be the amount of time it takes for the exponent to become exactly -1. So what would t have to be to make this exponent become exactly -1?
R times C.
Yeah, if you plug in R times C for time, you get RC over RC, so you get just 1. They cancel out. So the resistance times the capacitance, if you actually work out the units for that, resistance times capacitance, that is ohms times farads, gives you a value in seconds. Ohms times farads equals seconds. So that's an important thing about how the units work out. But if you multiply the resistance times the capacitance, you get an amount of time, and that amount of time is the time constant. It's the amount of time it takes for the current to decay to 37% of the original. It's also the amount of time it takes for the charge to decay 37% of the way, or to 37% of the asymptote. The important thing is, though, you're not measuring charge from ground level. You're not measuring charge from 0. You're really measuring the difference between the value right now and the asymptote. So if you take a look at this difference, so the charge starts off this far below the asymptote. A little later, the charge is now this far below the asymptote. Later still, it's now this far below the asymptote. And then this far, and then this far. So what's decaying is not the amount of charge. The amount of charge is growing. What's decaying is the difference between charge and asymptote. This far from the asymptote, then this far, then this far, then this far. The difference is what's decaying. And so that's what we'd be applying the idea of time constant or half-life to. After one time constant, like for instance, we start off, the current starts off this far above its own asymptote. You measure everything from the asymptote. One time constant, RC, will be some amount of time. That's the amount of time it takes for the amount to decay to 1 over E, about 37% of the original distance from the asymptote. And then one time constant later beyond that, 2RC, two copies of the time constant, you decay to 1 over E of that amount. In other words, 1 over E squared of the original, because you're dividing by E twice. And it just keeps shrinking every time constant forward into the future. And the charge should have the same time constant. Every aspect of this system that's decaying has the same time constant. It's decaying at the same rate. So the charge also has a time constant of RC. After one time constant, the amount of charge is going to be a certain value such that this difference, not the amount of charge, but the difference between the charge right now and the asymptote is exactly 1 over E of the original difference. One time constant later, at time equals 2RC, this new difference is going to be 1 over E of this, which means 1 over E squared of the original difference. So this is the whole idea of time constant. It's just the amount of time it takes to decay to 1 over E of the original difference between the value and the asymptote. And we usually write that as tau. So the time constant, in the case of a circuit with just a resistor, a capacitor, and optionally a battery, the time constant is always going to be resistance times capacitance. If you've got several resistors, as long as you can combine them all into one total equivalent resistor, like if you've got maybe several resistors in series and then a capacitor, you can just add those resistors together. Then you can just treat this as the total resistance. There's also ways of combining capacitors into just one big capacitor, so this could be the total capacitance. But if you've got a more complicated circuit, you'd have to use other methods. But as long as you can reduce the circuit to just one resistor, one capacitor, and optionally one battery, the time constant will be exactly resistance times capacitance. So large resistance means it takes a long time to decay because the current's flowing slowly because of the large resistance. Large capacitance means it takes a long time to decay because it takes a long time to fill up that very large capacitor. If they're both large values, it takes a really long time to decay. If they're both small values, it takes a very short time to decay. So very weak resistance, very small capacitance means it's going to just zip up to the asymptote almost instantly. Any questions on that so far? All right, then that's it for today. Mess around with the loop rule equations to get some more practice with that. It might help to just draw out some circuits and then try writing out the loop rules for those. Solve them if you can. And we'll look into some more examples of exponential decay next time.
Thank you.
You're welcome.
Thank you.
You're welcome.